over the other side, you can think of it as a force. So the classic problem is the Chandrasekhar problem. So there are really three generic problems in rotating convection, and there's quite a big literature on all three. So I'll just describe what they are, first of all. The first one is the Chandrasekhar problem, the way you've just got a plane layer of fluid here, two parallel plates, gravity is downwards, the rotation is upwards. So this would correspond to what's happening near the pole of a planet, not, of course, to what's happening near the equator, because near the equator the gravity is perpendicular to omega, but near the pole they're parallel. So you heat it from below, and then eventually as you heat it up, if delta T exceeds a critical value called the Rayleigh number, given by the Rayleigh number, that then starts to convect. And so that's the classic problem of the rotating plane layer, and I'll say quite a bit about that. That's a picture of sort of what happens from an experiment. So that's left is Baynard convection with no rotation. So that's what happens, what you get, the cellular pattern that you get if there's no rotation. That's in Mercury, I think. Yeah, I think so. This one, on the other hand, is what happens when there's a rotation, fairly mild rotation here. And you can see straight away that the length scales have shortened, so that here you've got quite decent sized length scales, here you've got quite a lot of rather small length scales, and that's a feature that we'll see of the effect of rotation, smaller length scales in the rotating case. So plane layer is one big model. The next big model is Annulus. So let's just make sure we understand what the Annulus is. So we're just looking at the fluid in this region here, yeah, between these two concentric cylinders, and it's not got flat ends, it's got ends which are sloping at a small angle chi. And this is a very nice theoretical model because you can capture a lot of the spherical properties of spherical convection with this model, but it's mathematically a great deal simpler, which is why Fritz Busse started analyzing it. So physically, you get most of the physics of rotating spherical convection in this model where you don't have to mess around with the mathematical complications of spherical geometry. But the sloping end walls are going to be very important, and I'll explain why. So that's that, and then the final model is the classic convection between concentric spheres. So this is basically the model for all dynamo models. So they're all done in concentric rotating shells. So in all dynamo models, we're looking at a fluid layer there, and the radius ratio can be anything from 0 to 0.9 or something like that. And there's an inner core boundary and a core mantle boundary there, and the outer core is all here, and there's an inner core there, and it's rotating about the polar axis, like so. So those are the three classic mathematical problems, theoretical problems. So what actually happens in a sphere, let's just give a sort of overview, first of all, of what actually happens. We'll go through the maths a bit later. So that's a sketch of what happens near the onset of convection between rotating concentric spheres. This is Busse's picture. And basically, somewhere in the middle, you get these long, thin columns developing, so that the heat is being transported by rotational motion along these columns, which is spiraling up. So the fluid motion is actually spiraling up the column, and it goes over and spirals down an adjacent column, and it spirals up from there and in from there. And there is sort of experimental apparatus to do this. So there have been some experiments which you can look up in rotating shells. And these things are typically driven very, very fast because to get the thing moving very fast, the centrifugal acceleration is actually much larger than gravity, so that the effective gravity is in this direction because of the very rapid centrifugal force. So this is the exact opposite limit to what I was talking about when I was neglecting the centrifugal force compared with the gravity here. the gravity is neglected compared with the centrifugal force. Fritz Busser and Chuck Carrigan took these lovely pictures where you can see those columnar structures. The fluid is seeded with aluminium flakes and lit up, and so you can actually see the flow structure, and you can see these Busser columns are actually occurring in the convection. So we know that from experiment that is actually what is happening, and that's of course what's predicted by theory as well. Now, in order to explain why the columnar structures appear, it's necessary to do a bit of maths. And I'll tell you a bit about the Proudman-Taylor theorem and the vorticity equation. So the first thing we do is to take the curl of the equation of motion, and we're going to ignore magnetic field to start with, and we're going to ignore, that's all we've really ignored actually. We just ignored the magnetic field, and I've just taken the curl of that equation there. So that equation there, yeah. So the pressure, of course, disappears. We're assuming it's constant density fluid. We're thinking of water or mercury. So take the curl, that goes away. I'm ignoring that. So I get left with terms this, and this. And that produces me this, where zeta is the vorticity. So that's the vorticity equation. And that's the vortex stretching term, which is very important. So that comes from the curl of omega cross u. When you take the curl of omega cross u, the important term is minus 2 omega dot grad u, which turns into that, minus 2 omega du by dz. And that's a thermal wind term, which I'll talk about. We're going to ignore those, first of all. So the first thing to do is to think about omitting the buoyancy term, and we'll think of the viscous term as being small, and we'll just look at these equations first of all. And actually, the first thing we do is to consider what are called slow steady motions. Slow steady motions are motions at very low Rossby number, where these terms here become small compared to that. So that is sort of in some sense much the biggest term, and because there's nothing to balance it, it's got to be 0 in the way of these things. So since all the terms that are got here, we're either ignoring them or we're considering them to be very small here, then the dominant term is this one. Therefore, this thing has to be 0, which tells us that the motions have to be independent of z. So the velocity has to be independent of that direction parallel to the rotation axis. And of course, for a columnar motion like that, those spiraling columns, that's pretty well true, because they're pretty well the same all the way along the roll. So it's doing its best to get into a Proudman-Taylor state. So this actually was discovered, this mathematics was done by Proudman in, I think, about 1916. And Taylor, well, nobody really believed it. It's so completely, it's completely unintuitive to imagine that motion can move along in columns independent of z. I mean, that's not what fluids do. You look around and it doesn't seem to be doing that. And that's, of course, because we don't usually see rapidly rotating fluids. So Taylor did some experiments. Now, the main purpose of the experiments was to find out where Proudman's mathematics had gone wrong. And he discovered, much to his surprise, that Proudman's mathematics was actually correct, and that things do actually move around in columns. And I've got a little movie here. Now, the first one movie here is, this is a non-rotating fluid movie. So here we've just got a tank of water here, which is not rotating. And we just put a little bit of dye in it. So let's see what happens. Yeah. So somebody just stirs it up a bit to give it a bit of turbulence, a bit of motion. And in they pop a little bit of red ink there. And you can see that's the Z direction there. And that's looking down from above. So it's a cylindrical tank, yeah. And you can see that, as you'd expect, the turbulence mixes it all up in 3 dimensions, in the Z direction and in the X and Y directions, and you end up with the sort of uniform sort of dilution, much like you would if you had an enhanced viscosity. And that's sort of where the ideas of turbulent viscosity come from, because they sort of mix the fluid up. So that's what happens in a non-rotating fluid. Now let's do exactly the same experiment, but now the tank is, whole thing's on a rotating turntable, and the chap who's going to put it in is standing on that rotating turntable, and the camera's on the rotating turntable. So everything's in the frame of reference of the rotating frame of reference, and he's going to do exactly the same thing. And now let's see what happens now. Okay, stir it up just like we did before. Then goes the green dye, and a very different picture is emerging here. First of all, you can see that these things are developing into sheets straight away. And look at the fine filamentary structure. The motion is two-dimensional when looked from above. So this is a two-dimensional motion, not a three-dimensional motion. And look how different that is. These very, very fine streak structures develop and persist for really quite a long time. That tells you straight off that rotating fluids are very, very different from non-rotating fluids. Sorry?
What is the depth?
We saw a little move a bit on that, and that was a side view of. So that was a camera that was looking sideways on. So it's about that's looking from above. That's looking from above. If you look down, these are actually sheets of fluid. Basically, that is basically a sheet of red fluid, and that would be a sheet of green fluid there. And those sheets are moving around, and as I said, it's a two-dimensional motion. So that shows you really fairly dramatically that the motion has gone from being three-dimensional down to two-dimensional in the most direct way possible. Okay, I think that's about a fairly good, yeah, that's a good place to stop, because I'm going to explain a bit more when I come back about the mathematics of why it's two-dimensional and how you can break the two-dimensional and what happens if you start putting waves on that system, and that'll be the next time. Okay, fine, good place to stop. Let's have some coffee and tea.